Hello, ladies and gentlemen. I hope you're all doing well. We're up to question C3 on our 2012 Canadian Open contest. So let's dive in and take a look, shall we? Alright, so C3. Let ABCD be a parallelogram. We draw in diagonal AC. Looks like we draw in a lot of things. A circle is drawn inside ABC, tangent to all three sides, and touches AC at point P. And then, we jump into A without these other two circles and this line here. Okay. Just because they've got the whole picture drawn, let's read everything. It is a later question, so we might want to consider the whole thing. So A would be prove that DA plus AP is the same as, not BC, DC plus CP. Okay. So that shouldn't be too bad. It's only worth 2 marks. What would B be? Draw in the line DP. Okay, there they've added DP. The circle of radius R1 is drawn inside DAP. Anytime we talk about circles tangent to all three sides, I immediately like drawing in radii from the center, and we're calling that length R1. Okay. A circle of radius R2 is drawn inside DCP, tangent to all three sides, so we'll draw those in. And remember that radii, when connected up to tangent points, make right angle triangles. So these are R2s. B part, we want to prove R1 over R2 is AP over PC. So the ratio of those lengths is the same. So we'll have to think, how can we get equations involving multiplications and divisions that can relate these radii and these side lengths. So we'll get to that, I guess. And then C, what do we want? Suppose that DA plus DC, so these two sides here, is equal to 3 times the diagonal AC, and DA is equal to DP, so then we'd have an isosceles triangle. And let R1 and R2 be the radii defined in B. Determine the ratio R1, R2. We may have to use what we learn in B. We'll see. Okay. So C part would have 2 options. Look at the radii themselves or talk about AP to PC, which may or may not be easier. We'll find out. But we can just start off with A, and we'll draw just the picture they have described ahead of time, which has only the one circle. That's a terrible circle. I apologize to everyone I've ever known. Let's add that back in. I'll just thicken these points up here. Alright, remember, drawing the picture is only going to be useful to you. As long as it's a halfway decent picture. Now, it is a C-part question, so we should be drawing and explaining, but you don't have to get out your straight edge and compass or anything like that. So we've got P here. We want A, D, no, D is down in the corner. I've got these wrong. D, it was AC was the diagonal we're given, and B. Okay, so I'm going to exploit some circle properties. If I've got a circle and a point outside and I drop tangent lines, then these tangent lines are the same length. So this is a consequence of what we call power of a point, or I think it's called power of a point, but basically the tangent lines. So point to tangent C equals the same length on both sides. I think this has a proper name. I just honestly cannot remember what it is right now, but the point is we can say that this length here is the same as this length here. This length here is the same as this length here. And we got these 2 green lengths here. Not sure why I started with 3, but okay. So we get all these pairs, and then we also know it's a parallelogram. So we might call these lengths X, Y, and Z is going around like that, or maybe X, Y, Z the other way. It doesn't really matter. Okay, so we got X, Y, Z, and then, but AD is equal to BC, because it's a parallelogram. And not AC, DC, well, CD is equal to AB, because it's a parallelogram. Now, AD is going to be X plus Y. So DA plus AP, I think, is how they have it written. So DA is going to be the same as BC, so that's X plus Y. Plus AP, which is Z. And then DC plus CP is, well, DC is the same as AB, so that's Z and Y. And CP should be X. Yes, it is. So let's say same value. I was going to say same length, but same value. Okay. So that's A part pretty quickly, and then they add in these other circles. So we'll draw our picture again a little bigger, hopefully a little bit better. I'm always optimistic that I can draw these things better over time. Nope. I'll redraw it again. Try and make it more the size of their picture. What I'd really like is an ability on whatever software I use to be able to copy and paste pictures from one file to another, and then I could just copy their picture and not have to deal with these pesky circles being inscribed in triangles. That's a wish list of mine, though. Maybe someday if I made ad money, which I don't, I could get software that works like that. Oh well. I'd say that's pretty decent. I mean, the curves are kind of sketchy, but that's okay. The curves of the circles. Again, it's a picture. It only needs to have meaning to me when I'm doing a contest, or me and you when I'm presenting these things. We might not even need this other circle over here. But what have we got? Right angles here. Right angles here. Right angles here. So the blue lengths are R1. And then, where can we go from here? So I want R1 over R2. I want to show that's the same as AP over CP. So like I said when I was just sort of reading through the question, what I'd really like to think of is sort of multiplicative statements. Multiplicative ways to relate lengths, side lengths, and these in-circle radii. And that's exactly what these circles are. They're called in-circles because they are inside the triangles and they touch all sides of the triangle. So, and circle geometry isn't the most common thing done in high school nowadays, but if you're serious about math contests, you should pick up an older geometry textbook, maybe from the 70s or 80s, or find a PDF online, and you should learn a little bit of circle geometry. I have books somewhere here that has some of that old stuff. I can't see it right now, and we won't go through it, but I do have an older book, I think by a fellow named Howard Eves. Don't quote me on that. Anyway, so I'm trying to think of relationships involving in circles and side lengths, and one that comes up to me comes to mind immediately would be in circle radius times the semi-perimeter, which comes up occasionally in Heron's formula, gives me the area. Okay, now why might that be relevant? Well, the picture here does not do it justice. So what if I just sort of cut out part of the picture, took it out, and rotated it? So we're just going to cut out that picture, but we're going to rotate it. So we'll put D up here, A here, C here, we'll put P about here. So just taking same picture. I hope I have the colors right. Okay, same picture, but when I look at it like this, I think about, well, AP, which I think we called Z, and CP, which we called X. These look like bases for these triangles. But then there are other ways to make these triangles. Let's use some purple. If I connect P to the center of this, A to the center of this, and D to the center of this, I've got this R1 here. And I can see that, for example, the area of APD is 1/2, so we'll do this triangle, so 1/2 DA times R1, plus this triangle, so 1/2 AP times R1, plus this other triangle, and you'll notice that these R1s, because they're perpendicular at their points of tangency, they are providing heights for each of these triangles. So that's DP R1, which is better expressed as 1/2 DA plus AP plus, I guess we'll do PD, times R1. But this part here is the perimeter. Dividing it by 2 is what's known as the semi-perimeter. Okay? So this gives me one way to express the area here. And it's a nice multiplicative statement. I'm multiplying R1. So if I could get an area for CPD, maybe make a nice ratio here, that might be in some way helpful. Now, notice also, what have we got in here? We'll use green. DA plus AP, we just in A said that this is the same as DCCP, and there's going to be a DC and a CP in this triangle over here. Plus a PD, but that's going to be common to both of them. So let's say area of CPD is going to be 1/2. We don't have to do the whole explanation again. We can just say 1/2 the perimeter. So DC plus CP plus PD times R2. Great. Well, we could say by A, DC plus CP plus PD, put these guys in brackets, is the same as DA plus AP plus PD. So the area of APD over the area of CPD is going to be 1/2. Let's call this amount, I was going to say P for perimeter, but maybe, well, I don't know. X, Y, and Z are already used, so W, I guess. 1/2 WR1 over 1/2 WR2, which is just R1 over R2. Great. I have the sort of expression that we've got here. But how can I bring in AP and PC? And this is why I rotated the picture. They form bases. So if instead of drawing in the circles, get CP and A here, we say something like drop the perpendicular from D to AC, and that'll be somewhere in here because this is the bigger one. And we could call this point E, or I guess Q would be fine because of P and Q. So then we have a height H. H is DQ. Now I want some ice cream. And then the area of APD is 1/2 APH. And the area of CPD is 1/2 CPH. And if I divide them, the H's cancel out, the halves cancel out, I get AP over CP. And that tells me that R1 over R2 is AP over CP. All right. And that's all we needed to prove for B. All right, what about C? So this should be a little harder. Let's get this out of the way so I can read the full question again. So DA plus DC is 3AC. Okay. So we're relating the sides of the parallelogram to the diagonal, and we also know DADP is an isosceles triangle. So just to use the picture that we just had, so this would be equal to, well, we already used the double earlier, so use 4. But those two sides are the same, and actually that would mean that Q is the midpoint of AP. Which might be helpful. I don't know. We might not need the isosceles triangle this way. There's other things we could do. I mean, we might be able to sort of do a reflection or something like that. Not entirely sure what exactly we're going to do here, but I mean that's an observation. We want to use this fact. They give us this. We want to use this somehow. And we've also got dA plus dC is 3 times the diagonal, and we have R1, R2. We just want the ratio again. So I would say, just based on what we've had presented, so we'd say by B it suffices to find AP over CP. Okay, so we just need to find them. That ratio. Now, should I look at this picture? I mean, that's got the isosceles triangle, but is there anything else I could learn here? Well, definitely we have the isosceles triangle, but what do I want to make of the dA plus dC? Got dA dC in A again. And of course, AP plus CP, or AP plus PC, should be AC. So, let's see what we can get. So by A, dA plus AP is equal to dC plus CP. So dA plus AP plus dC plus CP, which I think we called this x plus y plus z, where, what was it? PC was x, and so really we're trying to find the x over z ratio. Or z over x, my mistake. I'm not sure whether or not this will help, but just trying to recall everything we learned in A. So this will be dA plus dC plus AP plus PC. I guess, yeah. But that's 3AC plus an AC, so this is 4AC. And so that should be 2 times x plus y plus z. So 2AC is x plus y plus z. I guess that's true. I don't know how helpful that is. Of course, it's also... Yeah, so x plus y plus z is 2AC. That's 2 times AP plus PC, which is 2z plus x. I don't like, we're going to have a y stuck around here. So we got x plus y plus z is 2z plus 2x. So y is going to be equal to z plus x. So I guess that's some kind of a relationship. I guess. Not exactly sure where to go from there. But that's definitely true. But dA, we also learned in A part that dA was equal to something. Alright, what did we learn? dA was the same as BC, and we had what? X, Z, X, and a Y. So this is X and Y, but we've also got X and Y down here. Is that helpful in any way? Well, that is true. I'm not exactly... Maybe that isn't the right way to use dP being equal to dA. I don't know. Maybe the isosceles triangle might help. So we know dA equals dP. Therefore, the Q that we dropped from B is the midpoint of AP, since it was an isosceles triangle. Or since it is an isosceles triangle. It's only an isosceles triangle for this part of of C3. So let's just redraw that picture again. See if maybe we can come up with something else to do. So we had Q about here. We had this height. And this is xy, sorry, x plus y, and this is x plus y. And this is z. Although I guess we could say z is y minus x. And if it's a midpoint, this is y minus x over 2. This is y minus x over 2. So I guess we could get the height by using the Pythagorean theorem, maybe? We also have, this is y plus z over here. And this is x, so this distance here, x plus y minus x over 2 should be y plus x over 2, which incidentally is half a dp. But I think we can get two Pythagorean theorems. So use Pythagoras on triangle DCQ and triangle D, I guess we can do PQ. So we get h squared, which was that height, we used that in B part, is going to be x plus y squared minus y minus x over 2 squared. It's also going to be y plus z squared minus y plus x over 2 squared. Let's multiply through by 4 on both sides. So 4 x plus y squared minus y minus x squared is equal to 4h squared is equal to y plus z squared, 4y plus z squared minus y plus x squared. That way we can at least bring this over to the other side and say we've got 5x plus y squared is equal to 4. Now, should we really, I guess y plus z is the same as 2y minus x. So 2y minus x squared, so 4 times that, plus y minus x squared. Just rearranging everything so it's all positive. We might have to rearrange. Now we've got one equation and 2 unknowns. We can't solve for x and y, but remember we don't actually want to. We want to solve for, I guess we should probably keep everything in terms of z. I'm going to change it so it's z because we actually need z over x. But a little carried away there. So what's y in terms of... Yeah, so we can instead say z is x plus y. No, y is x plus z. That's what it is. So we got 5, 2x plus z squared is equal to 4. This will be 2x minus an x, so it'll be x plus 2z squared plus z squared. Yes. Okay, so let's finally expand this out. 5 times 4x squared plus 4xz plus z squared is equal to 4x squared plus 4xz plus 4z squared plus a z squared. So we get 20x squared plus 20xz plus 5z squared is equal to 4x squared plus 16xz plus 16z squared plus z squared. So we'll get 17z squareds minus 5z squareds. We will get 12z squareds. Let's bring it all over to the right-hand side. So 12z squared well, now that I think about it, maybe we should bring it over to the other side. Yeah, so 16x squared plus 4xz minus 12z squared should be equal to 0. Definitely divide by 4, so 4x squared minus xz plus 3z squared is equal to 0. It's not the... Oh, sorry, this should be a plus, and this one should be the minus. I'm not entirely sure I can... Well, we rewrite the xz as 4xz minus a 3xz. Should be able to get a 4x and then an x plus z out of here, minus 3z x plus z here, 4x minus 3z, or x plus z is equal to 0. So, either z is equal to negative x, or 3z is equal to 4x, and then z is equal to 4/3 x. So this leads to two ratios. Zx is either negative x over x, which is negative 1, or z over x is 4/3 x over x, which is 4/3. But they're lengths, aren't they? But these are lengths. Therefore, x and z are both positive. So z can't be negative x. Therefore, z over x, which is r1 over r2, is 4/3 x over x, which is 4/3. Okay, kind of clean. Not what I would have originally guessed. Just with that 3 in there, I was probably going to guess, and based on this picture up here, which admittedly would not be a particularly accurate picture, I was going to guess it was probably a ratio of 2 to 1, but 4 over 3, it does not look bad at all. I like it. Nice question. So that's it for C3. Up next will be C4. We're going to finish off the 2012 open paper in the next video, so feel free to join me for that. And until then, take care. Have a wonderful day, as always.